With us is Professor Stefan Williams, Professor of Marine Robotics at the Australian Centre for Field Robotics. Also, he got his PhD from the same university, the Sydney University. He's right now the leader of the ACFR Marine Robotic Group, and he's the head of the Australian Integrated Marine Observation System Autonomous Underwater Vehicle Facility. He's one of the persons who has been researching and working with underwater vehicles, with underwater drones for more years in the world, I think. So, Stephen, we're here to listen to you. Thank you very much.
Okay, can you hear me? Yeah. All right, I want to start by thanking Patricia and the conference organizers for inviting me here today and the opportunity to come and talk to you. And I'd also like to apologize for my late flight yesterday and not being in the Systems of Systems session, which I saw that Joao introduced some great sort of perspective on marine robotics. So I'm going to talk a little bit about the work that we've done over the past few decades in deploying multi-robot systems for exploration in marine environments. Okay. All right. So as some of the other speakers have done, I guess they've introduced where they're coming from. I think I saw Arnan was from Melbourne, so I'm not quite the farthest away. I think Melbourne's a little bit further away. But I'm based at the University of Sydney at the Australian Centre for Robotics. We've been undertaking research in robotics for over 20 years, fairly significant budget, and quite a large group, about 130, 140 academic staff, research fellows, PhD students, and quite a strong complement of technical staff. So we have a big focus on really being out in the field, deploying systems, and really trying to work across a broad range of different application domains. And I like to put up this kind of montage of videos that I think highlight some of the things that we've done and that have had impact over the years. Up in the top left, you'll see an example of a mid-air refueling maneuver. There's two small unmanned air vehicles. One's trailing a little drogue. The objective here is a control system that will get those two vehicles to engage for refueling or exchanging information. In the top right, we do a lot of work in agriculture, looking at deploying machine learning algorithms, onboard platforms, doing very high precision agricultural processes, whether it's manual intervention like this example here, where the robot's going in and digging up weeds. So using classifiers to find the weeds in the crop, or in the next little bit, you'll see precision spraying, where the robot's putting a little bit of fertilizer or herbicide onto the crop. We do a lot of work in autonomous driving, and my own work is predominantly focused on marine robotics. So I could talk, at length about all these different domains, but today we'll focus on the underwater environment. And I found this figure online. It was produced by the U.S. Geological Survey to kind of capture what we mean by ocean research. Where does this happen? What are the sorts of questions that we like to think about? And I'm going to frame my talk around this figure, because I think we've kind of worked in a lot of these areas. We've done a lot of work in the continental shelf, looking at coastal processes, understanding coral reefs and kelp forests and things like that, and using robots to help science in that perspective. We've done some work in deep water environments, helping to understand underwater geological processes. And more recently, we've been working up in the near-shore shallow environments. And then I'll sort of talk about a couple other things that I think aren't maybe captured in that figure. Our work over the past 20 years is really focused on developing platforms and sensors, really understanding how we can take novel sensors and integrate them onto our platforms, not only vision, but sonar, acoustics, hyperspectral. We've done a little bit of work with computational imaging. We focused a lot on navigation and mapping, on really helping our robots achieve their objectives and building detailed maps in the environments in which they're operating. We do a lot of work on planning and control, both on the platform, but I'll also show some of the work we've done in thinking about at a campaign level. How do we deploy these robots to collect the most useful information from the point of view of the objectives of the vehicles? And then a lot of my students have been motivated by the data analytics. So we collect a lot of data. How do we turn that into information that's useful for a range of stakeholders across areas in ecology, archaeology, geoscience, and we do a little bit of work with defense as well. In the introduction was mentioned that I've been part of this integrated marine observing system. This is a very large investment from the Australian federal government in it's a national collaborative research infrastructure program. So the physicists asked for synchrotrons, the astronomers asked for telescopes. The marine science community came together and said, okay, what do we need to actually understand the marine estate? And we designed this system that comprised moorings, ships of opportunity, gliders, contributions into the Argo Float program. There was some work tagging animals. And we came along and said, well, we've got an AUV, we'd like to deploy this and help support a better understanding of the biological processes that are happening, particularly in benthic environments. And so over the course of about 15 years, we were engaged in really deploying AUV systems all around Australia to help understand these marine environments, from tropical reefs up in the north down into more temperate regions in the south. And you can see by the years here that we've gone back on an annual basis to help understand changes in the environments that can be linked to changes in climate and oceanographic conditions. We've also had the privilege of being invited to do a lot of work internationally. So looking again at partnerships in ecology, archaeology, and geoscience. A lot of the work around Australia has been ecology, but we've done work in deep water geoscience around Japan and in the Mediterranean, some work in archaeology as well. So it's been really exciting to be part of a lot of this sort of work, deploying both our own vehicles, but also partnering with other organizations from around the world to help develop a better understanding of our oceans. So in terms of working on the continental shelf, we've had a fleet of different vehicles, and you'll see them throughout the course of this presentation. But I think this video sort of captures a lot of sort of the complexity of deploying vehicles in these environments. This is one of our first AUV systems. It was built at the Woods Hole Oceanographic Institution. It's hover capable. It's designed for operating quite close to the sea floor. This is actually a first century BC shipwreck site just off the island of Antikythera in Greece. And you can see the vehicle controlling itself over these relatively rugose bottoms, taking images of the seafloor, and then we stitch those together into big landscape scale models of the environment. The maps that we created of this environment were actually used to guide archaeological excavation, including the discovery of a nearly 2,000-year-old human remains that were found on this site following some of our survey work there. We've done a lot of work in coordinating multi-vehicle deployments, taking AUVs, gliders, surface vessels, and drifters. So we had some support from the Schmidt Ocean Institute a few years ago. We were in Hawaii, kind of invited all our friends to bring their kit along, and had a focus on surveying reefs around the Hawaiian Islands. And the objective really was to have a look both at the oceanographic conditions, but also the benthic environment. And this little Gantt chart on the bottom was sort of a tool we were using to kind of manually keep track of where all the assets were at any one time. But we did a lot of work on integrating all of the feeds from our vehicles, and I think Joao showed something very similar yesterday. But I think it should be noted that we're still in a regime of many people to robot rather than few people to many robots. And I think that's something that in order to really have impact in these areas, we're going to have to be thinking about how we can deploy these vehicles over longer periods of time with less reliance on expensive ships and expensive people. We've done a lot of work in the area of probabilistic habitat mapping, thinking about how we can deploy these platforms to collect information on benthic environments. So here you can see an example of a multi-beam bathymetric model of the seafloor. It tells us something about the structure of that environment. We've then deployed our vehicles. They go down, they take images of the seafloor, and we've used an unsupervised set of learning algorithms that both characterize the underlying bathymetry, but also find clusters in the imagery. So find images that are kind of similar to one another. And then we learn a relationship between those, the structure of the seafloor and where we're seeing particular types of habitat. And the labels here are added after the fact. So we're, in this case, not actually training the algorithm. We're just saying, show us things that look kind of similar to each other. Then we can label each image that we've collected of the seafloor and then do a prediction because we've learned the relationship between particular bathymetric structures and where we're seeing some of these particular images. And what you can see is, the kelp in that blue is sort of located on the upper parts of these reefs in, where there's enough light to support them. So despite the algorithm having no idea of what's in this data, it's actually pulling out ecologically relevant information. We also have notions of uncertainty, so in those models, so we can say, well, where is the model uncertain, and where should we go to collect more data? Now, not everyone has AUVs that they can deploy, and AUVs tend to be pretty expensive, largely because of the sensors we put on them. So what if we start taking off some of this complexity to kind of reduce costs? So we take off the DVL, we take off some of the thrusters, we might remove multi-beam. Can we turn this into something that's a little bit cheaper and that can be deployed in numbers, kind of working towards this idea of many robots to few people? And so our idea here was we were working with Chris Roman from the University of Rhode Island. He came along to one of our cruises with this imaging float. And in fact, I'll show, here's an example where we deployed this float. We also had the AUV running around. In fact, this was a completely unplanned video from one robot of the other because they were on a collision course and we had to retask the float to get out of the way of the AUV because we weren't actually coordinating them explicitly. But it got us thinking about how can we start doing some of this kind of imaging work with very simple robots. So this is a small imaging float. It's got a single degree of freedom, so it controls its depth, and then it gets pushed along by the currents. And so we built a few of these, and we thought, well, could we deploy these from an unmanned surface vessel? We threw this out into Sydney Harbour. Now, when everybody thinks of Sydney Harbour, they think of the Opera House and the bridge and all the beautiful environment. This is what some of the bottom of Sydney Harbour looks like. Not brilliant, but then we took these platforms offshore, got some very nice images of sponges and reefs. And then we took this offshore of Sydney with an unmanned surface vessel that included a little arm that could reach down into the water and pick up these floats. So you'll see on the left there, the WAM-V actually deploying the float, recovering it in the middle, and then putting it up into there's a little holster, so this thing can carry 4 of these floats. And we were working with colleagues at the University of Technology who were building models of the currents to help us figure out where we should put the floats so that they would drift over target areas of interest. And these deployments were done just south of Sydney. So we had some bathymetric data. We deployed the floats. They would go down, sort of drift along, and then come back up. They'd take images of the sea floor. We had deployed our AUVs in this area, so the little S-shaped path there is some previous deployments we've done with the AUV. We used our unsupervised clustering to find sand, reef, and kelp in the imagery that we'd collected. And we thought, okay, now we'll build a model of where we would likely find these different habitats. And so what you can see is the model prediction, so where we think we're going to see sand, kelp, and reef, and the uncertainty with that. And you can see that along here, we're really not sure where the transitions between different habitats are. So the objective then is to deploy one of our drifters, integrate new data, and then replan. So we've deployed a couple of drifters. We've put them in. You can see there's a little bit more green kind of appearing in the top middle of that prediction. The uncertainty's gone down. We might do this again. So we're kind of iteratively collecting data, building models, and using that to drive the further exploration. And what you can see is that this was the previous data that we'd collected with the AUV, and the model has basically told us where to deploy these vehicles or deploy the drifters in subsequent deployments. So we're really wrapping the modeling together with the planning to figure out where we should go to collect further information. Our most recent deployment, actually, was we've been in Tonga a few weeks ago. I had a couple of guys supported by a foundation called the Inkfish Foundation in collaboration with NTNU and the California Academy of Science. They're interested in documenting mesophotic reefs around the world. They're using divers, baited underwater video systems, and then ROVs and AUVs to get down into the deeper environments where they want to collect this data. And we took a pair of our small agile underwater vehicle systems. So these are AUVs that we've developed through a collaboration with Defense, actually, to look at operations in nearshore environments. But they were interested in very agile underwater AUV systems that could be deployed in nearshore environments, but we're also deploying them over complex reefs. So these vehicles sort of our hybrid between an ROV and an AUV. We're getting 8 to 10 hours of battery life out of the platforms. They have high-resolution imaging systems, a pair of strobes, and a full navigation suite. The work was done in the north of the Tongan Island chains, looking around some volcanic structures. And in this case, the kind of multi-vehicle aspect is not just multiple robots, it's robots and divers. And they collect very complementary information. So the divers are going along, they're collecting tissue samples so they can characterize particular corals. They're also doing some photogrammetry, very high-resolution photogrammetry of the transects they're surveying. And the objective of the AUV was to provide context by surveying, 6,000 square meters of sea floor, just mowing the lawn along these quite complex bottoms. So you can see the vehicle, it just goes back and forth while the divers are down collecting their information. And one of the things that we were doing here was trying to find areas that were suitable both for deployment of the AUV and the divers. The divers had limited time on the bottom. They're on rebreathers and down to 80 meters of water depth. They wanted to get multiple depth bands, so they would go down to 80 meters, run a transect, swim up a slope. So they wanted something that was relatively steep. Our robots, on the other hand, we don't want it too steep. So we did a little bit of work automatically finding areas of bathymetry that looked suitable for both the divers and the AUVs. Deployed over some quite a complex bottom. The vehicles have some obstacle avoidance sonars and a navigation suite that allows them to complete their dives. We take lots of images of the sea floor, and then we stitch these together into large-scale models in the environment. So you can see this is about 150 meters along this slope by about a 70 meter. It's almost 45 degrees, so it's quite a steep slope that we're reconstructing. And the divers have gone through and done their own surveys along this area of reef. So I guess here we're getting collaboration between, sort of implicit collaboration between the robots and the data they're collecting and the data that's being collected by the divers. And now we're working on stitching all that data together and georeferencing all the observations provided by the divers. So we go into deeper water environments. We've done a lot of cruises around the world and been invited to be part of some of those, deploying camera systems on both autonomous underwater systems and crewed platforms. This is some work we did in off of Okinawa in Japan. These are artificial hydrothermal vents. So the Japanese have gone in, they find areas of the seafloor that are hydrothermally active, and they've actually gone in and drilled into the seafloor to induce hydrothermal vent activity. And the white patches here are bacterial mats that have grown around the kind of hot water that's coming out of these vents. That thing in the middle is a drill guide that they use from a kilometer up to drill into the seafloor. And they're thinking about the potential for these hydrothermal vent systems often have very high mineral content. So there's implications for deep sea mining. But we went through, we had a couple of robots, one of which was deploying at high altitude over very large extents, but with lower resolution. And then we had some of our camera systems which were being used. And here they're classifying or manually finding different species of crabs and mussels and things in the data that they've collected. We also got invited to do some work in Greece. This is in the Colombo caldera, so this is an underwater volcano. Here we were looking at hydrothermal vent activities, so they were deploying gliders to characterize the oceanographic conditions, but also trying to find new vent sites. This was actually work funded by NASA in the context of potential interplanetary exploration of the moon, I guess Europa, where there's water-filled moon. So this was kind of an analog for that. Here what we did is we characterized the bathymetry using some of those unsupervised tools I showed earlier. We then had reference for where there was previously known hydrothermal vent activity, and then made some predictions about where they would find new venting activity. And in fact, they did find some new vents on this particular cruise. So really trying to use some of this analytics to help guide the exploration in these sort of tools. In the near shore, We've just wrapped up a project funded through a Defense Cooperative Research Center looking at littoral survey, so getting our robots up into very nearshore environments. We've done these sort of dense surveys up in the near shore. And in this case, what we're trying to help is look for unusual things in the environment. So we deployed a little acoustic tag into the environment. And our objective here was to find things that really shouldn't be or were unusual relative to the rest of the environment. So this is the imagery that we're collecting. So we're sub-millimeter resolution on the seafloor. And what we've done here is use some anomaly detection techniques, trained a variational autoencoder to reconstruct the imagery, and then to look for these outliers. So things that don't match with the underlying environment are poorly reconstructed by the features that are used, that are learned by this system, and it essentially finds areas that don't conform with kind of the rest of the environment. We deployed these sort of systems both looking at just the plain imagery, but also considering spatial context, and then did this also on a little crawler. And although it's hard to see, there are some mine-like objects in here that are kind of clustered in that space. So using some of these new machine learning techniques to find unusual objects without any prior training. We've also done some work deploying underwater hyperspectral imagery. So here we've got cameras and hyperspectral imaging systems. We use the cameras to do a reconstruction of the sea floor. We color the resulting 3D model, and in this case, we've put a little color target into the environment. And then these lines here are actually the hyperspectral line scans, which we've colored according to the RGB intensities. But in fact, each pixel in each of these lines is capturing 1,000 distinct wavelengths. And we've done a lot of work on characterizing the inherent optical properties of the water to allow us to reconstruct these, use this hyperspectral data, and then looked at the, estimating the attenuation factors across different wavelengths to allow us to reconstruct the actual reflectance of targets on the ground. Another interesting thing I think we've been doing is looking at intervention, so not just mapping. So how can we get in and do things with the robots? We've been working with a company in Sydney, Reach Robotics, who build small, lightweight electric manipulators. And here we're really focused on detailed models of the near field environment to allow the robots to start doing autonomous operations. So thinking about the coupled vehicle and manipulator system, tasks like grabbing ropes, turning dials, and things like that. So I think lots of exciting potential in this area. And to this end, we've been experimenting with some dense depth estimation tools. There's some really amazing work coming out of these monocular depth estimation tools where from a single image you can estimate the depth. So the third row here is from those images, it's estimating depth of every pixel. We're looking at techniques to integrate sparse information to get us metrically scaled data, and then to use that in the context of manipulation tasks. Wrapping up, another I guess thing that drives our research is the science drivers. So what are the things that the partners we work with are interested in? One of the things they're really interested in is repeat surveys, so change through time. So we can go through and build models of these environments. This is a survey of some kelp, some urchin barrens in the north of Tasmania. This is a survey taken during the day. We go back at night. We can sort of get to the same bit of the sea floor. And what you can see is that these urchins, which during the day hang out in the crevices, they come out during the night and they feed on the kelp and prevent it being. And I think about something like 20 to 25% of the Tasmanian coastline is now barrens as a result of changing climate. So really thinking about the relationship between climate and its impact on these environments. Here's an example of some coral bleaching where we've gone in 2010, there was a significant bleaching event in 2011. The plate coral has all bleached, but then you see these branching corals which are starting to grow in. So thinking about the dynamics of these environments and how they're reacting to their changing conditions. And then over much longer periods of time, this is some work that some colleagues, they took data. So here we've got data from all along the New South Wales and Tasmanian coast. They've identified these ascidians and other marine invertebrates. They've looked at building heat maps of the presence of these different species, and then they've used climate models to predict what's going to happen in 50 years in these environments as a result of climate change, to predict what the difference in these populations is likely to be over that much longer term. So I think the data that we're collecting really informing a lot of different science. And another example, we've used robots, but also PhD students who like to go out in these kind of environments. Here we've got a camera. We've wrapped a little line around a drum. They swim around. We get some GPS coordinates. We then use photogrammetry to figure out where the camera actually went. We can then build these sort of what we call our reef records. So these are, very detailed 3D models of that environment. And in fact, there's a team at Lizard Island right now finishing up our 2024 session. So we've been back every year. This is like we thought. The first time we went out there was a cyclone. We went out, collected some data. We thought, well, we'll document recovery. There was another cyclone. Then there's been a bunch of bleaching. So the dynamics of these biological processes are quite, there's a lot of complexity here. But you can see, at the end of a few years of bleaching in 2019, there was really not a lot of coral left. But then over 2021, 2022, you can see all this coral coming back. And of course, there's a lot of interest in machine learning and using machines to help interpret the data. So we've done a lot of work in unsupervised and supervised classification. Some of our recent work has really been thinking about domain adaptation. So how do we use classifiers trained on one data set, one set of imagery, and how do they translate across to new data sets? And we've made all this data available to the community. So we've built portals that provide access to all this data. So there's about almost 10 million images online. This tool has the capacity to allow people to do annotations and interact with the data. And there's also hooks so that we can put machine learning algorithms in the back that can be used to be deployed on all of this data. The sorts of things that we can do online here is label individual points. There's also some semantic segmentation tools that are built into this, and then some machine learning classifiers as well. And we can also get in and combine those detailed mosaics with the vehicle tracks and go to individual images. So all of the data we've collected through that IMOS program, and now we're starting to deploy this more widely. Almost done. And I'd say one other extreme environment that doesn't really get captured by the USGS is polar regions. And I think if we're starting to think about polar environments, this is an area where robots can have a really profound impact because it's a pretty miserable environment to be on ships. There's lots of weather, cold, there's some real challenges. And I think there's a huge amount of opportunity to use robots in these environments to help us understand the impacts of changing climate. It might not just be robots. It could also be other biological entities that are collecting data for us and going under the ice and really helping us understand what's happening in the polar regions. This is an image that one of my colleagues at Woods Hole produced, looking at the design space for Arctic sampling of AUVs. So if you look at this is sort of mass approximately on this axis and range. And this is sort of where AUV systems sit at the moment. If you look at the sort of nose and where the label is, that's kind of approximately. So there's some of these absolutely enormous vehicles which have long range but are very heavy. I think this is starting to be the area where there's a lot of exciting opportunities, where you're getting relatively low mass, but long range capabilities. And we've had colleagues deploying vehicles over tens or hundreds of kilometers, reducing the need for very expensive ships. And I think that also lends itself to fleets of these things, given that mass, in this case, is often correlated very strongly with cost. I gave a similar talk to this in Norway a couple of days ago, so I had to make it not quite so US-centric. And I'd also say that, our friend, the SEAL here, probably sits out here in terms of low cost and long range capability. So I think, lots of exciting things and potential in that space. I think there's, a great many things that have happened over, decades now of deploying autonomous underwater systems and robotic systems more generally. I think there's lots of exciting future challenges in long-range teams. So how do you get teams of vehicles out over long periods of time? Designing AUVs and unmanned surface vessels designed for particular mission objectives, and I think some of the things we've heard over the last couple of days in terms of soft robotics manipulation, I think there'll be some interesting opportunities there. Turning the data into useful information, increasing that operational tempo and the ratio of people to robots, and then I think some really great things happening with autonomous intervention, and I think taking a leaf out of Arlen's talk yesterday, we're always looking for good people to join us. So thanks for your patience, and I know I'm between you and lunch, so appreciate everybody's attention.
Thank you very much, Stephen. Is there any question in the room?
Great talk, and very quick question, I promise everything. You show some collaboration between divers and UMVs. Are you thinking about really trying to develop some real cobotics techniques between divers and vehicles, or is there really a need for that?
So I know there are some groups around the world doing that. So really starting to do gesture-based things to interact with the robots. In this case, they actually started out, the divers said, we don't want to be anywhere near the robots, so you deploy the robots, we'll be over here. And by the end of that 2-week cruise, they were doing operations simultaneously, not working together, but certainly the data they were collecting was very complementary. And in fact, by the end, the divers were so confident of what the robot was doing that they'd put the robot in, and then they knew where they were meant to be, so they'd go and kind of start doing their operations in while the robot, continued doing its thing. So we haven't done any specific collaboration between the robots and the divers, but I think there is potential for that sort of area. Yeah.
More questions?
So, it's on? Yeah.
Yep.
Thank you very much. Well, I knew what you were doing, but every time I see it, I think it's quite impressive. So thank you for the presentation. I was curious about what you explained about the anomaly detector, and I was connecting it to the biofuel.
Yeah.
The features that you are learning and that allow you to find these objects that shouldn't be in that place, do they still work when you have biofuel? And I'm asking because we have a project for detecting UXO, in which we have, there's marine life growing there. And I was wondering.
So I suspect if the things that are unusual also look very much like everything else, it's not going to come out. There may be opportunities to do that with multimodal data. So we're just using vision in this case. But I think if you had things that had different reflectance characteristics, either in sonar or potentially in the hyperspectral, and you started using those multimodalities to do something like that, to look for unusual things, I think you could make a lot of headway. And I think one of the challenging things is not wanting to rely on having to train it to say, this is the thing you're looking for, because all those unusual things are probably going to be a little bit different. So what we do is we actually train the autoencoder based on a subset of the data, and then when we deploy back into that environment, we can say, look for things that are inconsistent with what we've seen previously. Now that probably will have to evolve through time. So,
all right, very good. Thank you very much. We'll give it a thought.
Yeah, thanks.
Well, great talk, so thank you. Just 2 quick questions. I know we are quite short on time. So the first one is, because you've been operating in lots of different places, so what are your thoughts about, especially long endurance operations in places in which there's lots of ship traffic? Yeah. So there's the first one. And second one is, you also alluded to the fact that for example, for the drifters or the floaters, you're also taking into consideration currents to basically determine where to deploy the drifter so that you would reach this destination. The question is, are you also using that information about currents in your mission planning processes?
Okay, so one is the ship traffic for long-range operations. So we had a chat with a colleague from Southampton last week, or at the beginning of this week, actually, and he was telling us that they're doing deployments which are order 1,000 kilometers from shore, from near shore, vehicles going out, doing the surveys at multiple locations and coming back. Their strategy at the moment is surface periodically to get a GPS fix. They have no notion of what's on the surface. So the chance of a ship strike is small, but non-zero. We do have some funding through our defense, a thing called a Defense Innovation Network. A colleague in our electrical and computer engineering is building acoustic arrays. So the idea is to put an acoustic array on the vehicle to listen for potential ship traffic or noise so that we can stay submerged if there's vessel traffic in the area, or move away. And presumably you can listen for a lot of other things while you have those acoustic arrays deployed. And so, yes, we're thinking about it. Question number 2, remind me? The currents, yeah. So we haven't explicitly, the vehicle control systems compensate for currents to stay. We tell them, go on this line. They will then, the control systems are designed to compensate for that. Having said that, we did some work in a non-marine context for Qantas, one of Australia's main airlines, using probabilistic planning methods to do all their routing that use meteorological data to optimize routes. So Qantas now, all of their long-haul flights use those probabilistic techniques, and they reckon that they're saving order 1% of their fuel bill by using that meteorological information to increase efficiency. And they spend $4 billion on fuel. So, 1% of, it's a very big number. I think their return on investment for that research was quite good.
Thanks very much.
Thanks.